So, Jun'ichi.
Thank you very much. So, today I will be talking about risk bound for neural networks, but very simple neural network. So, before it, I will explain the collaboration with Andrew. So, this is a history of us. So, I graduated from the University of Tokyo in 1989, so in physics. So after that, I entered NEC Corporation, where I am a researcher of machine learning. So in this time, until this time, I didn't know about information theory. So, and after entering NEC Corporation, I learned information theory, and I met the MDL principle. It was very impressive to me. So because MDL principle is related to Occam's razor, it is related to the history of natural sciences. So it was very impressive. And maybe 1991 or 1992, you gave a talk at the University of Tokyo. So I attended his lecture. Maybe he didn't remember me.
Yeah, I remember that Amari invited me and that he introduced me to a number of students he felt had a lot of promise.
Yes. And in 1995, I had a meeting with Andrew at ISIT 95 in Whistler. So in this place, I proposed I would like to visit Yale University. So because I got the fund from NEC Corporation to go abroad. And and after that, I got my PhD, so Doctor of Engineering from Professor Amari. And just after that, I stayed Yale University, Department of Statistics, so from 1996 to 1997. Then we started the research on the minimax regret. This has long history. We are still working on that. And now we are finalizing. It's promising, I think. So, and 2006, I moved to Kyushu University. Left NEC Corporation. And after that, I visited here for the first time in 13 years. And we restarted our collaboration. So, and 2013, in August of 2013, so I invited Andrew in Tokyo and Fukuoka. So this is a picture at 2010. So we were young. So in Dana House, this is a picture. And he
couldn't even look up for the camera. I'm still looking at the paper.
yeah, he pretended to discussing. So this is a summary of our finding about the minimax regret. So, sorry. This one, okay. Considering this family, so possibly this is not the exponential family. Then, so usual Jeffreys prior doesn't work. But we can use the structure of a fiber bundle of local exponential families. Then we can nice mixture, Bayes mixture, which asymptotically achieves the minimax regret. This is well-known value. So this is a picture in Japan. This picture in Japan. So this picture, he is talking about sparse superposition codes. And here, it's some restaurant in Tokyo. And I think this is the best shot in Japan.
Can you go back to the previous one? I want to point out that Senghee Cho, I think, on the left, is
yes,
that right?
she.
And Cindy is over
yes,
there.
Here.
Yes, so Senghee on the left, Cindy on the right. And who's that next to me? Is that your colleague?
This is, he's Dr. Mori. And he gave a talk about spatially coupling codes. So, do you like this one?
I seem to.
And today's topic is tight risk bound of MDL estimators for simple ReLU neural networks. This is joint work with Jun'ichi Takeuchi, who also contributed to the work on sparse superposition codes. So the beginning of this research, so in 2016, I received an email from Andrew like this. Do you remember this one? So it says, sorry. So this is talking about a paper by the previous lecturer, previous speaker. So he obtained the risk bound like this. So here, usual bound, so we have D here. But this is log D, so this is very tight. But so only after 2019, I studied the paper. So this is the background of today's topic. So in 2019, I started the research on deep learning, so inspired by this paper and neural tangent kernels. So I expect that the MDL principle is a key. This is my policy. So I believe the MDL principle. So in 2021, we obtained some new finding about Fisher information of neural networks, but it is for very simple neural network. So approximate eigen decomposition. So it shows that eigenvalue distribution is strongly biased. So I think this can be utilized to obtain tight risk bound. So this is a review for very important results on MDL principle. So I'd like to introduce this theorem. This is originated in Barron and Koba, 1991. So this is this gives bound for MDL estimator. So the MDL estimator is defined using two-stage code. So two-stage code is designed like this. Here, this is data description length, and this is parameter description length. And we should choose the parameter minimizes this one. Then we have, so this is universal code for YN here. So, and here, the minimizer can be used as estimate given this training data. And for this estimator, we can have this kind of bound. This is risk, and d lambda denotes Renyi divergence between true distribution and estimate. That this is bounded by this one. So this expectation is redundancy of the two-stage code. This means that redundancy, the smaller the redundancy is, then this upper bound, the smaller the upper bound. And this is also can be translated like this. This is a well-known quantity, so index of resolvability. And so my plan is to use, in order to bound the risk of estimator for neural networks, to utilize this theorem. And so usually the quantization of V, this is a parameter space, is designed based on the Fisher information of B. Then so for this, about this theorem, Fisher information is very important. And this is some observation given by this paper. So it's very old. This shows the eigenvalue distribution of empirical Fisher information matrix of deep neural network. So it is important. So this scale is a logarithmic scale. And so this means that eigenvalue distribution is strongly biased. So this paper says that this phenomenon is very common in deep neural network. So I thought we can use this structure to bound the redundancy of deep neural network. So I thought that can we have a small redundancy by encoding only these directions, and we can ignore these small eigenvectors for small eigenvalues. So for this question, I think the answer is yes, if the Fisher information matrix is constant. So Fisher information matrix is constant for linear regression model. So this is very nice model for the analyzing this phenomena. So for this model here, so this X is row vector, and V transpose is column vector, and this is inner product. So this is usual linear regression model. For this model, Fisher information is calculated by this one. So this is so this quantity over sigma square equals the Fisher information of V here. And important is that this doesn't depend on V. So we can obtain this kind of bound for redundancy. The redundancy of this model, so linear regression model, can be bounded like this. So here, lambda I is the ith eigenvalue of J. J is the matrix here. This is sigma square times Fisher information. So in this bound, this is usual MDL-like term. So here we have D. And so this D denotes the number of eigenvalues around this. So we should encode these D directions. In that policy, we have this bound. So this is leading term. And the second term, this is extra one. This is arised from the ignored parameters because we didn't estimate those very large number of parameters. So we have here this extra term here. So this is a plant, and okay. And this slide explains our policy to design of quantization of parameter space. My plan is this: encode only the directions of these eigenvectors. First D, this corresponds to first D eigenvalues, and ignore the other directions. And J can be expanded like this. This is eigenvalue decomposition of J. So here, this is eigenvalue, and this is column vector, and this is row vector, and this matrix is projection matrix onto this direction of these eigenvectors. So we assume that U is unit eigenvector. Then J can be expanded like this. And then define this matrix K like this. Oh, this is my mistake. This tilde should be deleted. Then, so we use the new parameter U by this. So this is also normalization of J. And for the parameter for I is less than D, we can encode in the usual way. So precision, this one. This is in the two-stage code. This is the usual way. And when I is larger than D, we put the only one quantized point in the origin. In that case, we don't need code length. So in this case, code length is 0. It means that we can completely ignore P minus D parameters. So this is very important. And this is some details about quantization. And using the bound for redundancy, we can have this risk bound. This is direct conclusion of the theorem of Barron and Koba, 1991. So this risk is bounded by these quantities. The first is leading term of usually two-stage code. And this is the extra code. So this is some problematic. So we don't know about the behavior of this term. So if we increase D, then this beta D decreases. So because beta D is defined like this. Here, so in denominator, we have trace J. And so in numerator, if D equals P, this is the trace J, then D equals P, beta D is 0. So this beta D is a decreasing function of D. So this is important. If trace J is independent of P, and eigenvalue distribution is strongly biased, then this term and this term are negligible by controlling D. So in general case, we don't know this hold or not. But about this model, it holds. So this can be seen by the result of this paper. So for this neural network, so in this neural network, we fixed the weights in this layer, and target parameter is only here. So this is a linear regression model. And for this model, we can have this kind of eigenvalue distributions. And here, so these leading eigenvalues, the number of these eigenvalues is total this one. So D is the dimension of input vector. And this is detail of the setting of our analysis. And this is the main result of this paper, that this appeared in neural networks last year. So we have this kind of eigenvalue, this kind of expansion of Fisher information. Here, if, these vectors are defined like this. This is defined by using weight W. Weight W is weight of these regions. So in this expansion, if V0, WL, and these vectors form orthonormal basis, then this can be shown, and this is regarded as eigenvalue decomposition. But it doesn't hold in general. However, we can show that if W is drawn from this distribution, the IID, then so these vectors form in high probability, so nearly orthonormal basis. Then decomposition can be shown as eigenvalue decomposition. So using that result, we can use this kind of bound for risk. Here we have a leading term again, and in this case, D is defined like this. And this term, here this term we have epsilon 1, this is extra 1. This epsilon 1 controls the approximation of orthonormal basis in this expansion. So, and concretely, this beta is 0.03. This is independent of P. This is very important. And these terms are 1 over n, then it can be negligible. So main term is this one and this one. So I have 5 minutes only, so I can skip this one. And so remarks on this is important. So in this analysis, we assume V, the Euclid norm of V, so estimate target parameter restricted like this. So is this appropriate or not? So it is appropriate because this this fact. Let define, so this one, function norm by this norm. Then this can be evaluated like this. So it means that when V is restricted like this, then the function space is diameter of the range of FV is independent of P. So this is natural assumption. And here, so I'd like to give a note about the comparison with compressed sensing. So in compressed sensing, so the model is similar, but this is very different part. In the compressed sensing, usually we assume this one. So in this case, Fisher information is identity matrix. Then the eigenvalue distribution is uniform. So we cannot utilize the coding scheme for the neural network. But so it is important to use L1 control in compressed sensing. And so this is comparison with this paper. So their bound is like this. So they use L1 control, but this paper does not utilize the biased eigenvalue distributions. So possibly it would be possible to improve it by using the bias of Fisher information. And I have a plan about generalization, but I don't have enough time, so I skip it. So its conclusion. I believe that Andrew and I can finalize the paper on the minimax regret soon. And we can focus on the work for neural networks. And thank you very much for inviting me. Thank you.
Thank you very much. Do we have any questions? So if you were to parameterize the W's instead of having them fixed or normal, then your parameters would include the V's of the outer layer and the W's of the inner layer. Would the matrix that you're studying be, a kind of conditional Fisher information that would be part of the full Fisher information story in that case?
Yes, so I know one paper by Professor Amari. In that case, so Fisher information approaches to block diagonal like this. So this block corresponds to this output one node. So node by node, this approaches to block diagonal. So possibly, so Fisher information of single hidden layer captures the property of the full Fisher information.
Well, we can be so thankful to Amari. He's been working on this a long time. 2019, how old is he now?
Yeah, he's now doing research.
Is he in his 90s?
He's fine.
Is he in his 90s now? How old is he?
Yes, 2022, I had a discussion with him about this matter.
Wow, marvelous. So we can be very grateful to that heritage. Okay, any other comments or questions? All right, thank you.
Thank you very much.
Vince, you're so great.